So I'm Robert Simpson. I'm a lead software engineer here at Inoda, and I head up the digital twin team, which is responsible essentially for creating a sort of a virtual representation of our prime exchange device and how that fits into essentially power system networks and the models associated with that. Sure. So I think it's probably a good idea to kind of almost like start off with thinking about what a digital twin actually represents. So the way I think of it is that a digital twin essentially is a kind of a virtual representation of something physical. And whenever you can create something that's a virtual representation, you want to have some value from that. And really the value you get from these sort of digital twins is thinking about modeling situations, what-if situations, and provide a tool or a mechanism to actually allow you to not only kind of understand how the existing physical device operates, but also to think about different situations and test out different situations that can be done much more cheaply and efficiently and potentially less dangerously in a virtual model than actually doing it on an actual physical device. So, for instance, an analogy that I often use is actually thinking about, you think of Formula One cars. So Formula One cars, these teams all have digital twins of their Formula One cars. And it allows them to create and develop their cars to be better and faster in a much more efficient way than if they actually had to have physical devices and change those physical devices to think of what-if scenarios. So it's the same sort of approach. Kind of all we're doing is we're changing the actual kind of the physics underlying it. So let's say in a Formula One car, you care about airflow and downforce. For us, we're concerned about the performance of a kind of a power system essentially, and so there are kind of constraints there and efficiency metrics associated with that. But ultimately, really, what we're trying to create in the digital twin is some virtual representation of not only the device that we're creating here at Inoda, but more importantly, how does that device behave and react when you plug that into a real power systems network? And there are a lot of challenges associated with that, just the power systems network, because every network's different, and especially with the kind of introduction of photovoltaics and reverse power flow, things can be very challenging in terms of how loads and generation change throughout the day. So it's actually quite an interesting modelling exercise, this sort of thing, because in the past everything was, if you look at historical data, everything's very well defined in the sense that everyone basically turned their kettle on at the same time every day, and all these load profiles were very predictive and very kind of, everyone knew what was going to happen at any point in time. But now there's much more, let's call it randomness, in the loads and the way that reverse power flow happens, and so that's a challenging modelling situation for us, and that's some of the things we're trying to address here at Inoda.